Hi everyone, if you can hear me talk and you can see the video and it's working just fine, then it's quite helpful if you say something in the chat so I know I can start. All good. All right, very nice. So welcome back. Today we're gonna continue on with analysis of this exponential integral function, and then we're gonna talk more about another toy function in introducing this topic of exponential asymptotics, which is the complementary area function. Now, before I start, I realized last time I presented this very annoying calculation for the exponential integral involving the Stokes smoothing. I didn't do a great job, so I'm going to try to do it again today. And so it's quite painful, but it's worth doing it once and to do it for this simple example. And then we can all move on and apply the same technique to other similar problems. Now, what was the situation? So here we are. Okay, so this is this was our steepest ascent analysis of the exponential integral. You remember the idea was that we had converted it to an integral equation. And then we explained that if you're in the lower half plane, you have dominant contributions coming from the endpoints. But in this picture here, where your point moves into the upper half plane, then you have to include residue calculation. And what we were trying to do was to derive this residue without access to the original integral equation. We wanted to do it purely from the differential equation perspective. And we were going to do it by this process of estimating the late terms and then Stokes line smoothing. So this is the calculation that I want to do carefully now together. Every time I do this calculation, I'm always reminded of how painful it is. But let's try to recap the key ideas. So here's our differential equation. We're going to write this as our linear operator is equal to epsilon over 2. Okay. And then though this process, it doesn't care whether the problem is linear or nonlinear. So then you expand your solution into the usual series. You're going to truncate it at a point capital N that you're going to choose in a minute, and then write down a remainder. So you want to get the equation for that remainder. And in this case, if we substitute this into the ODE, you're going to end up with the linear equation for the remainder, linear operator applied to the remainder, so that's LRN now. But you're going to have the term which is epsilon to n minus 1 left over because it's not being matched by anything. So this will get you minus epsilon to the n times yn minus 1 prime. Okay, so now it's just convenient. Instead of having to take a derivative, we know that the equation epsilon to the n is balanced by this yn term on the right-hand side, on the right term on the left-hand side. And so we can write this as epsilon to the n times yn, just by the relationship between yn minus 1 prime and yn. And then the key is that we have an estimate of this thing on the right-hand side. We know how that diverges. So we can then estimate this. Now, in this problem, in the exponential integral, you know exactly how that term diverges for all n. In fact, you have the exact relationship. But you only really need an estimate, and for this problem, I'm going to write it as this. Now, I'm going to come back to this notation often for other problems in exponential asymptotics. It's going to be our convention going forwards. And so I've introduced to you a gamma constant and a chi function here. And for the case of the exponential integral, gamma is just 0 and chi is just z. So for the exponential integral, chi of z is just z and gamma is just 0. But it's useful for us to do this analysis kind of for a general divergence form, because we're going to find that many problems that we're going to work with, almost all problems, are going to diverge in this way. So just to clarify here, chi is a function of z. And I'm going to actually also multiply this, just so you can get familiar with the notation, with a prefactor lambda, capital lambda. But again, in this problem, lambda is just 1. But it's just good for me to get you used to this notation so that we can generalize this in the future. Okay? Good. So we have an estimate of this divergence. Now, the next step is for us to put in an ansatz for the remainder and try to derive its form. But the trick will always be that you want to choose n so that it's optimal. And the optimal point that you should choose it is such that the error is the least. And the heuristic is that the error is the least at the location where adjacent terms are approximately equal in the asymptotic expansion. And in the last lecture, we found that this optimal truncation point, n, is basically mod x over epsilon. This is just if you take the ratio of adjacent terms and take the mod of that and equate that to 1. And then you introduce a row where rho is just a bounded number so that it lands on an integer. Okay? Right, so the next thing we're going to need is, now notice from this relationship that as epsilon goes to 0, our optimal truncation point goes to infinity, which is what we expect, right? That's a property of being an asymptotic expansion. But the next thing we're going to need is we're going to need to stuff this quantity into the gamma function, and that results in a string of really annoying expansions for you to do. So you're going to need some kind of identity for the gamma function of n plus gamma. Okay, and you're going and then you end up having to use Stirling's formula for that. And I've given the identity within the notes, but I'll just write it down here. It's not hard to derive, but it's just quite annoying. So this is root 2 pi. And then it's mod x over epsilon to the n plus gamma minus a half. And then this is 1 plus, and then in brackets, rho plus gamma times epsilon over mod x. I'm going to erase that quantity on the right there. So just remember, whenever you see a chi, it's just z, and gamma is just 0, and lambda is 1. For the simple case that we're doing firstly. And so this is n plus gamma minus a half. And then this is e to the minus n minus gamma. It's a very annoying expression to work with because basically n is large, so you always have to ask yourself, how do I interpret this expression? Now this thing here, this quantity is actually e to the gamma plus rho plus order epsilon. So that can be simplified. And remember that n is basically this quantity here, mod chi over epsilon plus rho. Okay, so if I just put this expression underneath the curly braces into it, then you see that basically we have root 2 pi, this is twiddles. Do I want to simplify this? R over eps, okay, I'll keep it as it is for now. This is mod chi over epsilon to the n plus gamma minus 1/2. And then I'll just simplify this one as e to the gamma plus rho, and then this is e to the minus, this is going to be r over mod chi over epsilon minus rho minus gamma. So you can see that the gamma plus rho cancels with that gamma plus rho, which is why it was quite important not to consider it to be 1. You actually had to find the right factor here. Okay? Right. So we have an expression for the gamma function that we're going to use. There it is. Okay, so now we're about to put this into that, but we have to make a series of simplifications for the remainder term. Okay. Now, just so you remember what the end game is, I'll erase this one here, and I'll just erase that one there, and I'll just keep that remainder. Basically, the end game is, this is the picture we have in our heads. This is the z-axis here. This is the real z-axis. And we sort of know from our steepest descents that we're expecting that there's a Stokes line, this special transition line across the horizontal axis when z is greater than 0. So this is the imaginary part of z. So basically the idea is that we want to examine the behavior of this remainder equation as we walk from the lower half plane to the upper half plane. Okay? Okay, so let's think about the remainder equation here, LRN. Let me just write that out properly on the right-hand side here. So LRN is basically epsilon times Rn prime. Confuse it, plus Rn, yeah, plus Rn. And then that's epsilon to the n times all this nasty business with the gamma function, for which it looks like it's a bit impossible to simplify, but it will simplify quite nicely. Okay, now the first thing to remark about this Rn function is that it has a homogeneous solution, and the homogeneous solution is actually the exponential that we're expecting, right? So LRN equal to 0 has the homogeneous solution of Rn equal to a constant e to the minus z over epsilon. You can double check that yourself. So this is a bit suggestive that maybe, just for simplicity of the calculation for now, let's write our Rn, the actual Rn, which is being forced by the right-hand side here, let's write that as the homogeneous solution times a multiplicative factor. And the idea is that we want to check that this multiplicative factor is then going to go from 0 to a number across that critical line. Okay, so let's substitute Rn equal to a function that we want to find, this switching function, s of z, times e to the minus z over epsilon. And remember, I've just written it in this way just for generalization afterwards, but our lambda here is just 1, and this is, if I wanted to, I'd write this as minus chi over epsilon. So chi is just z. Again, I'm doing this because essentially for all kinds of other problems that we're going to do, it's always this form that we're going to be using. So but in this case, it's particularly simple. Okay, so when you substitute this Rn into the differential equation, basically, and then you have to take one derivative here, so you have to take a derivative of s and then take a derivative of chi. Basically, anything that does not have a derivative of s, that is just purely s, is going to disappear because of our choice of this as a homogeneous solution. So the ODE will then give you an equation for s, and it's going to be essentially, it's just going to be epsilon times ds dz times lambda times e to the minus, I'll use z's for simplicity here instead of chi's, and then is equal to the right-hand side. Now remember, we were assuming the divergence follows that law, and in this case, the lambdas disappear. they cancel on both sides. So we didn't really need to write them. And this is chi of z to the n plus gamma. I keep on going back and forth between using a chi notation and using a z notation. I'll just use a chi notation here, but whenever you see chi of z, you're seeing z. So, okay, immediately these can be canceled left and right. Okay, and then now you see that I'm going to put this form for the gamma function into the top there. Okay, so let's do that here. So I have epsilon to the n. I guess I have a minus 1 here from the left-hand side. And I have a ds dz. And then I'm just going to stuff this fella into the gamma function. So I'm going to have a root 2 pi mod chi to the n plus gamma minus a half. And then I have e to the minus mod chi over epsilon. The gamma plus rho cancels with the minus gamma minus rho there. And then I'm going to have a bunch of stuff on the bottom here. But I can just write this as mod chi times e to the I times the argument of chi all to the power of n plus gamma. All right? So now you can see this chi to the n plus gamma will cancel that chi to the n plus gamma, leaving us with a minus gamma to the 1/2 factor on the top there. I still have this weird argument that's going to stick around that I'm not sure what to do with. But sure, I can simplify it a little bit now. I realized where I screwed up. When I wrote down the identity for the gamma function, it was actually mod chi over epsilon to that factor, so I'm missing that on the bottom there. It was epsilon to the n plus gamma minus 1/2. Okay, that makes more sense. Okay, so you see this epsilon to the n cancels that epsilon to the n. And in the last lecture, someone had asked, well, why do you need to do this whole optimal truncation business? And the answer is that if you don't do optimal truncation, this remainder, by kind of properties of the asymptotic expansion, is always going to be the order of the term that you neglected. So it'll always be algebraic, epsilon to the n, or epsilon to the n with a shift. In order for you to get it to be exponential, you need to choose your n just right. And that's why you're seeing this kind of simplification. You see the epsilon to the n cancels with the epsilon n here. I'm left with basically root 2 pi over mod x. I have a 1 over epsilon to the gamma plus 1/2 factor on the bottom there. And then I have a e to the minus chi over epsilon and I also have an e to the chi over epsilon. I forgot to multiply this over to the other side. So there should be a e to the chi over epsilon from the left-hand side here being multiplied to the right-hand side. So that's plus chi over epsilon. And then I have that argument business, which, sure, I'll write it on the top here. I times the argument of chi to the n plus gamma, which again, is a bit mysterious. Okay. Now this guy is an oscillatory factor. And you see from this quantity, this important, so remember that for our problem, chi is just z. So you have essentially z over epsilon minus mod z over epsilon. And this is characterizing the rate of change of this switching factor s. And you see the kind of key insight, which is that this rate of change will be exponentially small unless you take your term chi, because this factor will always this factor here will always be bigger than that factor there, or rather be more negative than that factor there. So you always have this exponentially small business unless you take chi to be real and positive. If you take chi to be real and positive, then this term here will basically be the same as mod chi over epsilon. So chi being real and positive for chi being z is exactly that line there. So you've essentially detected it via the exponential there. Okay? Right. Well, what's the next thing we should do? Well, we'd like to basically produce a coordinate system so that we can skip along the line. So let's essentially do that by writing a coordinate system and introducing this angle theta. Okay? So you start with this equality here. Now for simplicity, I'm going to, at this point, convert to entirely using z's. Okay, so I'm going to use chi of z is equal to z. But you can do the argument in general without making this assumption. Okay? And I'm going to make a coordinate substitution and write that as e to the I times theta. Okay, which is the obvious thing to do. So note that your optimal truncation point is basically r over epsilon plus rho. Okay? And we're going to basically fix the r, the distance away from the origin, and rotate in theta across that line. So that allows us to convert the derivatives, d dz now, to d theta, and I have to do a little chain rule here. And that's basically just 1 over I times r times e to the I times theta d theta. Okay, so now I can put this change in derivative into this ds dz quantity, convert everything into d thetas, and then stare at that for a bit. Right? So if I put that in, I'm going to have ds d theta. I need to multiply this by I, multiply it by r, and this is a r to the minus 1/2 factor. So that should give me I root 2 pi times r, because remember mod chi is r, over epsilon to the gamma plus 1/2. And then let's just write our exponential. This is minus chi. Go ahead and write it as minus r over epsilon. And this will be chi, but chi is actually r e to the I theta over epsilon. Quite a knowing exponential of exponentials. And then this is minus I times argument of chi, which is just I times theta, to the n plus gamma, and remember n is r over epsilon plus rho plus gamma. Okay, quite annoying. And then I also have a factor of e to the I times theta, which comes up. So I think this becomes a plus I times theta here. Okay. So now what I have to do is I have to do a bunch of expansions because I'm going to profit from the fact that theta is going to be a small number. So theta will be small. But a lot of this stuff starts to cancel out because, for example, you see if theta is small, this is r over epsilon plus r over epsilon. And there's also an r over epsilon here as well. So you kind of have to put things together in the right way. So if I call this factor star, then this star is basically e to the r over epsilon, and then we have a e to the I times theta minus 1 minus I times theta rho minus 1. Hopefully that's right. Okay, and then now you get to expand this one here for theta small, so I have 1 minus 1 plus I theta minus I theta, and then the first term here is a minus theta squared over 2. Okay, and this one you're not going to care about. So at the end of the day, you get ds d theta is going to be I times root 2 pi r over epsilon to the gamma plus 1/2. Boy, oh boy, and then you have an e to the minus r over epsilon times I theta squared over 2. And then plus order theta, but then this one here, because e to the theta is just 1 plus small stuff if theta is small. So this one can be ignored. This one can't be ignored because it has an epsilon in there. And so you have to think carefully about the size of theta squared over epsilon. Okay, that's it. So at the end of the day, this is basically the final, well, the near final result, the result at which we can kind of point to it and say, hey, look, there's something interesting that's happening there. Okay, let me erase everything else and let's have a look at this thing here. Okay, so this is basically quantifying the change in the prefactor as you go up through that line. And essentially the idea is that this guy is exponentially small. Sorry, there's no I items here. Once I did the Taylor expansion, it's just minus r over epsilon times theta squared over 2. The idea is this is exponentially small except in a small region around the axis. And the size of that region you can see from here. It's basically where theta squared over epsilon is order 1. So this suggests that there exists a boundary layer when theta squared over epsilon is order 1, where this change in the prefactor is no longer small. And so you can then rescale everything. So let's let theta be root epsilon times a new theta and zoom in near that region, near the axis, right? And so then I have dd theta is basically dd theta bar, and then I have a 1 over root epsilon scaling from there. Okay, and then that will cancel the epsilon to 1/2 there. And then this will basically give me that the rate of change of the factor s is essentially I times root 2 pi r over epsilon to the gamma times e to the minus r theta squared over 2. And there's our Gaussian looking thing. Just so you remember, for the case of the exponential integral, gamma is just 0, but we've kept it general again for epsilon to the gamma here. Okay, so at the end of the day, we've come out to this, and then now we just have to integrate this from one side of the from one side of the line to the other. So this tells us that this s is basically the integral of this quantity. And it's essentially, so the integral from a point from minus infinity, so minus infinity is down here. of this quantity. So this is root 2 pi I times r over epsilon to the gamma, integral from minus infinity to a point theta bar here, and then this is just a dummy variable. Let's call it t squared over 2 dt. Okay, and then under the right, the usual substitution for the Gaussian, if I integrate this from minus infinity to positive infinity, that gives me the answer I need, which is just a jump. Okay, so this tells me that the jump in this quantity, I'll just end up with a root 2 pi factor, I think, a 2 pi over r factor or something along those lines. And if I just take the infinity value minus the minus infinity value, which is just 0, then across that line, I basically have a change of 2 pi I once I do the appropriate coordinate transformation. It's actually 2 pi I over epsilon to the gamma, but in the case of the function we're looking at, it's just 2 pi I because gamma is 0. Okay, so this is basically the end result of this painful set of calculations, which is at the end of the day, your remainder term has switched on as you go from below the axis to above the axis. It's switched on basically 2 pi I over epsilon to the gamma e to the minus chi over epsilon. And in this case, for the exponential integral, is just 2 pi I e to the minus z over epsilon over 1. And that is the final result. Okay? Okay, so a few comments about this process. By the way, let me just draw for you what has happened. So the picture you might want to have in your head is that this is basically new bar, theta bar, and below the axis you're 0, and then above the axis you increase to basically 2 pi in magnitude. So if I plot the magnitude. Okay. So this is what's known as Stokes switching. So that's why this process is called, optimal truncation and Stokes line switching. It's basically you have optimally truncated the asymptotic expansion. You've then zoomed in near the Stokes line and you've smoothed out that Stokes line. Now there's a few things to note from this process. Okay? The one crucial thing is that the switching is smooth, right? That for essentially for epsilon smaller and smaller, the neighborhood in which it switches, so if I plot this not in terms of theta, but in terms of theta bar, but if I plot it in terms of theta, then this ramp up, this is of order root epsilon. And so you could technically, if you had an accurate enough computer, you can do this experiment where you study the properties of the function, and you would be able to show that if epsilon gets smaller and smaller, you see this ramping up of this hidden exponential, and the ramp up size is basically, the ramp up speed is basically root epsilon. Okay? Now originally when Stokes had studied this kind of process for the area equation that we're going to study next week or in the next lecture, Stokes had thought that this switching on occurs discontinuously, right? So that basically when I'm below the axis and as soon as I cross this line, I switch on a term discontinuously. We see here that the switch on occurs smoothly, but in the limit that epsilon tends to 0, it appears to be discontinuous. But if you zoom in just the right way, in a little boundary layer near the origin, near the Stokes line, you see that the switching on happens with root epsilon. Now the second comment to make is that this process that we've applied, you can kind of revisit the process and ask yourself how much of it depended on the fact that I was working with an exponential integral. I was working with something quite simple. And the answer is sort of, and you can see my suggestion of treating things in a more general way with the gammas and with the chi's. The answer is that actually this switch on that happens, this 2 pi I over epsilon of the gamma, is almost universal. That you can take a large class of asymptotics problems, right? Much more complicated problems than what we've seen here, and you can essentially show that the switching almost always happens in this way. In other words, if you can characterize the late terms of an asymptotic expansion in terms of these gammas, in terms of these chi's, you can almost skip this whole procedure of the Stokes line smoothing. And it's almost a universality that it's always going to come out to this kind of equality. And that's often what's done for more complicated problems. You don't really go through this process for more complicated problems, though you can, but you'll find that actually the steps that you take are very, very similar. Okay? All right, so we've essentially looked at this exponential integrals, and we've done it in a variety of different ways. So this problem y prime plus y is equal to epsilon over z. This is the simplest such problem that we can apply these techniques to because, well, it's as simple as a first order ODE. We can write down the exact integral. We can do the expansion for the asymptotic expansion to all orders without any trouble. We can study the integral using steepest descents, and then now we can study it using these kind of beyond all orders, these exponential asymptotics, by smoothing the Stokes line. What we're interested in now is how deep this rabbit hole goes. Can we try this with second order problems? Can we try it with nth order problems? What happens if it's nonlinear? What happens if it's a partial differential equation? But the essential idea is that the spirit of what we've done is true in general. Okay? Right, so for the second part of this lecture, I want to give you another toy example. The next one we do after this toy example is actually the area function. So originally, the Stokes phenomena was derived for the area equation by Stokes in the mid-1800s. The area equation is actually a little bit harder than some of these early examples, so that's why we're leaving it until a little bit later. But the next example I want to look at is related to the complementary area function. So I have a differential equation now, epsilon squared phi double prime plus z times phi prime is equal to 0. So this is a second order differential equation, and I have a condition at the origin, which is just epsilon root pi over 2. And then I have a condition at positive infinity, and it's basically 0. Okay? So you can directly integrate this function, and it's related to this complementary area, this special function, the complementary area function. But the spirit of what we want to do is the same as for the exponential integral. We want to try to write down the integral expression for this problem, study it using steepest descents, and then see if we can derive the same process without the integral. Okay? So this function is, you can integrate it once and then integrate it again, and you can write it as a Laplace type integral. So I can write phi of z as the integral from a point z to infinity of e to the, in the notes I use f of k over epsilon dk. This is epsilon squared, and f of k here is just minus k squared over 2. So it's the integration of a saddle, basically, and there's a saddle point. You can look at where f prime is 0, f prime of k is equal to 0 when k is 0. So off the top of your head that when you do the steepest descents, there might be some special considerations with k is equal to 0. Okay? This is also a problem where we're going to have Stokes phenomena and Stokes lines and all that business, and we basically want to predict all this phenomena that occurs. Okay, let's have a look at how steep descent occurs. Remember that we're trying to study the asymptotics in the z-plane of this function, and we're going to start off starting with, let's say, z positive and real, and then we're going to ask ourselves what happens to the steep descent process as z continuously deforms in the complex plane. All right, so let's start with the first picture. I'll see if I can draw the picture on the board in a minute. Okay, but this is essentially the picture of the steep descent path for that integral. Okay, I'll draw the picture out on the board, but what you're seeing on the top right there is essentially the k plane, the integration plane. You essentially have to integrate from a point z, which is, for example, one of the black points on the top right is the point z, and you have to integrate to positive infinity for your integral. And you want to do this along paths of steepest descent and get an approximation. The picture that you see on the big picture you're seeing is essentially the magnitude of the integrand. You can think of that as the magnitude of the integrand. It's essentially the real part of the exponential argument. So again, the idea is that you want to take your original contour of integration, which is one of the black points, this is the value of z, and go to positive infinity. And you want to do so following lines of steepest descent or ascent, at which point you can isolate what are the key contributions to the integral. Okay, and in the picture, the hatched regions that you're seeing are basically valleys where the integrand is small. So you essentially need to always land in a valley because otherwise your integral is not defined. Okay, so let me plot that again for you here. So this is the real k plane and the imaginary k plane. Oops. Remember, the integral I is a function of z. It's an integral from z to infinity of e to the, was it k? It's f of k, I think. F of k over epsilon squared dk. Yep. Okay. And the kind of pictures we had, don't know whether I can draw it without looking at the reference diagram. Let me see if I can do that here. Basically a saddle. It's a sad face on that axis here. It's a happy face on this axis. My goodness. To give you a minute, I have to struggle through this. Okay. Hopefully my picture works now. So. Okay, here we are. All right, so what you're seeing in this picture here is the k plane. This is the real part of k going that way. The imaginary part of k goes that way. And then this is the magnitude of the integrand. So essentially it's the real part of f. Okay, so the integration path let's take a point z. You can take a point z along the axis, but it's a little bit more illustrative to see off the axis. But if the point z is off the axis and in this upper half plane, then you just want to integrate from the start point all the way to the end point. And the line of steepest descent is given by, so these lines are given by where the imaginary part of f of k is constant. Okay, so you can check that there is indeed, just by looking at the formula, if you just put this into Mathematica or another plotter, you can plot the constant contour, and there's indeed a constant contour that goes from z all the way to infinity. And so for this situation, I of k, I of z is just going to be dominated by its endpoint contribution. So you're starting from a point here, and you go to infinity down in the valley. All the dominant parts of this, the dominant contribution to the integral happens exactly at the endpoint z. And you can derive this by integration by parts, if you like, in the usual way. And then you find that if I, under one integration by parts, I have epsilon squared e to the minus z squared over 2 epsilon squared over z plus dot dot dot. Okay, so it's a bit weirder because it's your base expansion. The usual asymptotic expansion is not occurring in powers of epsilon. It's basically powers of epsilon times a prefactor, which is exponentially small, but it doesn't really matter. Every subsequent term is always going to have that exponential on top of it, and then it's going to be an algebraic expansion in powers of epsilon. Okay, and if I like, you can refer to the notes for the full expansion, but it looks something like this: e to the minus z squared over 2 epsilon squared, and then a power series in even powers of n, okay, times some. Let's write this as an of z, but I won't put in the details. Okay. The picture that you had seen before had shaded in this region here because that was a valley. So you're starting high here and then low there. And then similarly, we had shaded in this region on the left here. That was also a valley as well. Okay? So now the obvious question is, what happens when you start to move z around the complex plane? And as you might imagine, the danger happens when you move z into the left half plane here. So if I move z into the left half plane, because in order for me now to start from an integration from a point z to a point infinity, so remember this is the original contour of integration. It's some path that goes from z to infinity. I want to deform this, but I can't just, I always have to deform into a path of steepest descent. And in this case, the path of steepest descent goes left first. It goes up to a saddle point and then down. And you see that in this picture on the right here, you're going to start from a point z. You have to integrate to the valley at minus infinity, climb back up to the surface to the origin, and then go down to positive infinity. Okay, so the picture is here. So you see that if I start with the black point in the upper half plane, I first go down to the valley at minus infinity, at which point I'd say that there's a contribution from the endpoint at z. I then climb back up to the saddle point at the origin, and then back down. So when I perform the asymptotic approximation for the integral, I'm going to have two contributions. I'm going to have my usual endpoint contribution from the black point in the upper half plane, but then I'm going to have a saddle point contribution that I have to compute as well. Okay, so So if z is in the left half plane, I'm going to have my usual contribution, which I just erased, but I can write that as e to the minus z squared over 2 epsilon squared times epsilon squared over z, plus dot dot dot. So this is all from the endpoint. Right, so this is the endpoint contribution, which sometimes I'm going to call that as the base series. That's the usual asymptotic approximation that you develop. But you also have a local saddle point calculation that you have to do, and is essentially just the integral from minus infinity to positive infinity of e to the f of k over epsilon squared dk. And that's just essentially a Gaussian, so you can double check what that is for the given k, but it's root 2 pi epsilon. Okay, so it's similar, it's the same idea as for the exponential integral. What was different, well, the series are a bit harder to manipulate in this problem, but you're seeing this key idea, which is that sometimes when you move z around the complex plane, you can switch on these exponentially small things. Notice that this left half. Yeah. Okay. I was gonna say that. Notice that this is exponentially small. You're gonna see in a minute why that is. But essentially, when z is along the imaginary axis, this term here is going to be of a different size than when z is along the positive axis. All right, I was a bit confused there. So I'm going to plot the graph for us, the next graph, and hopefully that explains why I was a bit confused. Okay, so the next graph we want to do is just the real part of z, is the imaginary part of z. And the idea is that if I'm in the right half plane here, then my asymptotic approximation is just this base series, because it's just the endpoint contribution of z. Right? It's just this approximation here. But I know that if I cross this line here, the imaginary axis, then I have to switch on a contribution. So I have phi base plus root 2 pi times epsilon. Okay? I can verify that when I switch on this quantity here, right, z is basically I times t along the imaginary axis. So that tells me e to the minus z squared over 2 epsilon squared is e to the t squared over 2 epsilon squared. So at the point where I'm doing the switching, this base series is actually huge, right? It's exponentially large. And that's why this guy is exponentially small compared to this guy when you did the switching. I was a little bit confused. I was looking at this factor. I said, oh, why is this minus z squared over 2 epsilon squared? That seems to be a lot smaller than this one. But the key is that when you do the switching, at the point where you switch it on, this thing here is smaller than this thing here. Okay? You can see that, in fact, in the picture, in the graph here, that in this picture, note the saddle point is actually going to be lower than the black point above it. So the contribution from the saddle point, you had to cross the saddle point to get to positive infinity so that you can perform your contour integration. But the key is that when you do that switching, that saddle point contribution is actually exponentially small compared to the black point above it. Okay? Now, if you were to move the black point in fact, to the diagonal, to 3 pi over 4 in angle, you would find that that black point is actually the same height as a saddle. So that explains the next picture that I'm going to show you here. Right here. Okay. So at this argument in Z, you can verify that this term is actually going to be the same order as that term there. Okay? And on this line here, on the negative real axis, you can actually verify that 2 pi epsilon, root epsilon, is actually bigger than this base term. Right? Because this is exponentially small now, and then this is order 1. So they've swapped in magnitude. And then they swap again at the dashed line. Right? So in this region here, I'm going to write phi base plus root 2 pi epsilon. I'm going to do this convention where I write the order of the contribution to be first or second, depending on whether it's bigger or smaller. And then across this line here, which is the Stokes line, that contribution switches off. Okay, so go back to your integration plane and ask yourself, well, what happens if I now have rotated around almost in a circle? Well, if my point Z, one of the black points, lies in the right half plane again, I just can go straight to infinity. And I just have the single contribution. Okay. So this is the final result. This is what's known as the Stokes line. And this is what's known as the anti-Stokes line. The Stokes line is where an exponential switches on or off. So you see, I started off with the base expansion. I crossed that Stokes line, and I switched on an exponential. It doesn't look like an exponential, but it is an exponential. It's exponentially smaller than this one. The anti-Stokes line is where your two contributions are the same magnitude. So at this dashed line, these two series are actually the same in contribution, in order of contribution. But then they swap. And as I go in the lower half, into this left half plane, close to the axis, actually, the thing that I switched on is now bigger than the thing that did the switching. They become the same size, again, at the anti-Stokes line along this dash curve, and then they switches off. This exponential that I switched on is then switched off, and I'm returned to the base expansion. Right? So this covers all those important concepts that we've introduced. The idea of a Stokes line. We have this swapping of exponentials. Again, just to reinforce the idea that exponential asymptotics, just because something is exponentially small doesn't mean it's not important. Right? Here, indeed, this root 2 pi epsilon is exponentially small. Here, when it's switched on, it's also not present on the right-hand side. But you see that in order for us to gain an appreciation for the complete picture, you need to include it. Right? That's how you get back to the original series. The other thing that you're seeing is that the analysis of this is no different than what we had before using the exponential integral. It's a little bit more complicated because you have an endpoint contribution and then a saddle point contribution, whereas for the exponential integral, it was an endpoint contribution and then a residue contribution. But the basic idea is the same between the two problems. Right? Well, the next thing we want to do in the next lecture is we need to start off with the second order differential equation, and then we need to use our exponential asymptotics without the integral, see if we can derive this switching. And the procedure is basically almost exactly the same. What makes it more complicated is the fact that the late terms diverge in a slightly more complicated way. It's not as simple as the exponential integral. The ODE is a little bit more complicated. It's a second order problem compared to a first order problem. And so we have to do some transformations to apply our asymptotics to. But then the switching you're going to find is almost identically the same. It's the same kind of principle of optimal truncation and Stokes line smoothing, and then you'll be able to come out with this kind of quantity. Okay? We're not going to do that analysis in full details because it's going to take us a long time to do it. But in the next lecture, I'm just going to write down for you what the late terms are. We're going to see these gammas, we're going to see these chi's that we saw in today's lecture. And then we're going to go on to the area equation, which is another interesting problem to understand the concepts of exponential asymptotics. All right, thanks to everybody, and I'll see you in the next lecture.